Hello everyone, my name is Kanokwan Kratuloek. I am from King Mongkut University of Technology, Thonburi, Bangkok, Thailand. Today I will present about develop regularized Krasnosel'skii-Mann iterative algorithm for approximating fixed point of English non-expensive mappings. My content will be presented in 5 sections. In the first section is objective. In the second section is introductions and preliminaries. In the third section is main result, and the last section is conclusions. In the section 1, objective. For approximating the fixed point of English non-expensive mappings in Hilbert space, we consider a developed regularized Krasnosel'skii-Mann algorithm for which we prove a strong convergence theorem. And we also empirically compare the rate of convergence of the developed regularization Krasnosel'skii-Mann algorithm with the simple Krasnosel'skii fixed point algorithm and conclude that the latter one more convenient. Section 2. Introductions and Preliminaries. The problem of existence and approximations of fixed point of non-expensive mapping is important, as it has important applications in various areas of research, and many problems can be regarded as fixed point problems for appropriate non-expensive mappings. Convex feasibility problems, convex optimizations problems, monotone variational inequalities, image recovery, signal processing, and so on. However, the study of fixed point of non-expensive mapping is not trivial. Indeed, if C is a core-non-empty subset of a Ballena space X and a mapping T is non-expensive, it is known that T may remain a fixed point. It may happen that even T has a unique fixed point, iterations of T may not convert to a fixed point. For example, I'm interested in the case if T has a unique fixed point, are secant xn's of the Picard iterations, a map is Tx equal to 1 minus x on interval 0, 1 with the usual norm, which gives for x0 equal to 1. A unique fixed point of a map is 1 over 2. Subsequent x to n equal to 1 and subsequent x to n plus 1 equal to 0. Then, the sequence xn is not converted to 1 over 2. This shows that T has a fixed point, but the Picard is not converted to a fixed point. To construct the convergence for approximations of fixed points of non-expensive mapping, instead of Picard iterations by using Krasnosel'skii-Mann algorithm, specify this. This simple but powerful algorithm is usually called demand iterations, or the Krasnosel'skii-Mann iterations, or simple Krasnosel'skii iterations in case lambda n equal to lambda. However, the Krasnosel'skii-Mann algorithm has only weak convergence under contained conditions. For a proof strong convergence, we developed regularized Krasnosel'skii-Mann algorithm. Let H be a real Hilbert space, and a mapping T be a nonlinear mapping. Support alpha n, beta n, and theta n are secant interval 2, 1. Then, sequence xn specify this. Converges strongly to a fixed point of non-expensive mapping T. Let X be a linear norm space. A point X belong to C is called a fixed point of T, provides Tx equal to X. We denote by fixed T specify this. A mapping T is said to be non-expensive if specify this. And a mapping T is said to be an enriched non-expensive or B enriched non-expensive if there exists B belong to non-negative, such that When b equal to 0, any non-expansive is a zero English non-expansive. However, the strong convergence result obtained in the main result for the Krasnosel'skii iterations is tributary to the additional property of demi-compactness of the English non-expansive mapping T. We need the following: demi-compact. Let H be a Hilbert space and C a subsequent of H. A mapping T is called demi-compact if has sequence U and is a Brother sequence in H, and sequence T UN minus UN is strong convergent. Then there exists a subsequent of UN which is strong convergent. In the theorem 1, we want to show the set fixed T or fixed point of T is a non-empty convex set, and Krasnosel'skii iteration sequence Xn specify this converge strongly to a fixed point of T. In the section 3, main result. For theorem 2, we show that the developed regularized Krasnosel'skii-Mann iterative algorithm converges strongly to a fixed point. This is a statement of theorem 2. Following conditions C1, C2, C3, C4, and C5 as a true for a proof subsequent Xn, Yn, and Zn generated by developed regularized Krasnosel'skii-Mann iterative algorithms define this converge strongly to a fixed point of T. Theory 1. Theory 1 is special case of theorem 2. As T is a non-expansive, T is a zero English non-expansive, and therefore the constant mu defined in the theorem 2 equal to 1. So, this algorithm leads to algorithm 2. By theorem 2, if we give that C a bounded chord-convex subset of H and a mapping T be a English non-expansive mapping, then fixed T is a non-empty convex set and the sequence Xn, Yn, and Zn generated by the developed regularized Krasnosel'skii-Mann iterative algorithms define this converge strongly to a fixed point of T, and alpha n, beta n, and theta n are sequence of real number in interval 0, 1. Specify conditions C1, C2, C3, C4, and C5. In example, show that the theorem 2 is an effective generalization of theorem 1. Let X equal to interval 1 over 2, 2 be enrolled with the usual norm, and let a mapping T be defined by Tx equal to 1 over X. Then, T is not non-expansive. T is a T over 2 English non-expansive mapping. And fixed T equal to 1 or fixed T has a unique fixed point. In the table, we present a comparative study of developed regularized Krasnosel'skii-Mann algorithm involved in theorem 2 and 3, and of simple Krasnosel'skii algorithm involved theorem 1. For the case of a non-expansive function T in example 1. For the numerical experiments, we consider different values of parameter alpha n, beta n, and theta n, and lambda, and of starting point x0. By n, we denote the number of iterations needed to obtain the fixed point with 6 exact digits. In the table 1, numerical experiment for Krasnosel'skii iterations and starting point x0 equal to 0.5, you can see. When lambda equal to 1 over 2, it shows iterations when number 4. When lambda equal to 1 over 3, it shows iterations when number 1. When lambda equal to 2 over 3, it shows iterations when number 13. When lambda equal to 3 over 4, 4/5 and 5/6 is not show iterations. The speed of convergence of Krasnosel'skii iterations for considered LH non-expansive mappings depend on parameter lambda and starting point x0 equal to 0.5. The more Laplace Krasnosel'skii iterations correspond to the value 1/3 of the parameter lambda. When one iterations, we obtain the exact value of fixed point. In this case also, convert quickly for value 1/2 of parameter lambda. After 3 iterations, we obtain the fixed point. By analyzing the result in Table 2. Table 2 is numerical experiment for developed regularized Krasnosel'skii-Mann iterations starting points x equal to 0.5. Note that the developed regularizations Krasnosel'skii-Mann iterations converge very slowly in comparison with the simple Krasnosel'skii iterations. In order T case considered for parameters lambda, for parameter alpha n, beta n, and theta n, for starting value x0 equal to 0.5, the developed regularized Krasnosel'skii-Mann iterations converge extremely slowly. Developed regulation Krasnosel'skii-Mann is not show iterations of fixed point. In section 4, conclusion. Based on numerical experiment report here, we can conclude that for approximating the fixed point of some LH non-expansive mappings, it would be more convenient to use the Krasnosel'skii iterations than the developed regularized Krasnosel'skii-Mann iterations. Thank you for your attention.